let's talk about carboxylic acid derivatives and their reactivity, really the take-home message here. I want to ask a critical question about carboxylic acid derivatives, inasmuch as carboxylic acids have this general function or structure here, of which there are a number of different derivatives that exist if we were to replace this portion right here with some other type of atomic arrangement. And if we replace this section right here, we get different derivatives of carboxylic acid. And if we were to replace that OH with a Cl, we would have an acid chloride. Let's make the camera adjust here. And if we were to replace this OH right here with this RC double bond O like this, we would have an anhydride. And if we were to replace this OH portion with this entire R, so the replaceable portion being this chlorine, or the replaced portion being this acetate group, or if we were to replace that with an OR, we would have an ester. And if we were to replace this with NHR, we would have an amide. And then there's also this nitrile that doesn't necessarily look like a carboxylic acid derivative by first appearance, but certainly in its reactivity, we have shown in these videos that it has really the same properties as a carboxylic acid derivative, and as such we would expect it to react in the same fashion, and we categorize it as a derivative as such. So I want to ask a critical question, which is ultimately the take-home portion of this unit, which is, when we look at all the reactions that these species could undergo, there's a lot of them. And certainly there's some redundancy here that we can talk about. But let's just take a look at an acid chloride. Holy crap! An acid chloride could be used to make a bunch of different species. 1, 2, 3, 4, 5, 6, 7, 8 total reactions that have to go along with reactions of acid chlorides. If we look at anhydrides, it seems to me like your textbook is suggesting that it can undergo 1, 2, 3, 4, 5, 6, 7, 8 different reactions. Interesting. If we look at esters, reactions of esters, it looks to me like esters could be used to make 1, 2, 3, 4 different species that aren't carboxylic acids. Interesting. And it looks like amides could be used to make 1 different thing that isn't a carboxylic acid. Curious. How come as we proceed from left to right, there are fewer and fewer and fewer reactions that these species can undergo? Let's take a look. Acid chlorides. Acid chlorides can be used to make carboxylic acids. I'll keep saying that, but that's not really the point I'm at yet. They can be used to make esters. They can be used to make amides. Primary amide, secondary amide, tertiary amide. So you would expect these to all be grouped together. And they can also make alcohols, aldehydes, ketones, and such. Anhydrides can be used to make, interesting, in conjunction with an acid chloride can be used to make an anhydride, but they can only make esters and amides. And it appears like esters, when we're looking at just the carboxylic acid derivatives, can only make amides. And when we look at amides, they can't make any other carboxylic acid derivative. So what the heck is going on here? Amides can make, using SOCl2, nitrile. Well, it turns out is if we critically look at the species that are attached, so if we critically look at the things that are attached at this position right here, with this question mark, you would notice that as we progress from right to left, we start seeing an increase in leaving group ability. Check this out. If we were to react this species to make one of these other species right here, we would displace a chlorine atom as a minus. That's a pretty good leaving group. If we were to displace this anhydride with maybe something else in these carboxylic acid derivatives, the leaving group from this species would be this acetate group. And this thing is resonance stabilized. And so when a piece of something can leave a molecule, and it can be stabilized when it leaves, well, then it's likely to leave. And so this is a pretty good leaving group. Not as good as a halogen, but certainly this molecule, this leaving group has developed, or possesses rather, a way that this species could stabilize itself once it's left. The leaving group over here is an OR. Well, that's not necessarily a good leaving group, and in fact, we would call that a good nucleophile. Uh-oh. NHR? Well, if an OR is a good leaving group, then an NHR is a very fantastic leaving group. Let's ignore the nitrile for right now, just for a second. Another way of looking at the same exact idea, and you'll never see this in a tech book, but increase in staying on ability as we move from right to left. Sorry, scratch that, reverse it, flip it. From left to right, we increase the staying on ability. So if the question is, well, I guess like, hey, check this out. These species are made as better leaving groups. So if we're asking the question of how come acid chlorides can be used to make anhydrides, esters, amides, and nitriles, they have, they can make 1, 2, 3, 4 different carboxylic acid derivatives. How come anhydrides can only make 1, 2, 3 different types of carboxylic acids? How much derivatives? How come esters can only make amides? And how come amides can't really make anything except nitriles? Why is that happening? How come you can't convert an amide into an acid chloride? Well, in order to react an amide and convert it into an acid chloride, if you were to do that, you would require this amide to react with Cl-. And if it did, using the same reaction mechanism we'd always anticipate seeing, nucleophilic attack at the carbonyl, break of the weakest bond, reformation of the carbonyl, let's see what would happen. Nucleophilic attack at this position, break of that bond, we would absolutely see this occur. And then once this carbonyl wants to reform, the chlorine is the better leaving group, and as a result, we would just displace the leaving group and get right back to where we started. Well, if that's the case, because this is a weaker nucleophile, it will not outcompete the staying on ability of the NHR bond, or the NH carbon bond, and as a result, even if we were to see the chlorine add to the carbonyl, we wouldn't see it stay there, because once that carbonyl reforms, it's going to jettison the better leaving group. And so when we look at the reactivity of these carboxylic acid derivatives, this I just posted online. It's for you. This is the way that things go. As you move from left to right, you can make any carboxylic acid derivative, provided you have a carboxylic acid derivative that features a better leaving group than the thing that you are trying to add. If you have a chlorine leaving group and you want it to react with an alcohol, an ROH, well, that ROH is a better nucleophile than the Cl minus. This the O carbon bond is a better staying on, stronger bond than the carbon-chlorine bond, and as a result, you can't compete. And you would definitely jettison this chlorine in the presence of oxygen to make this ester, but you could never use a chlorine to jettison this OR to go backwards. And so what you learn from this chart, and certainly there's a lot going on here, but when you learn from this chart is these are the most reactive species, and they become less and less reactive as we progress from left to right through these carboxylic acid derivatives. And what I mean by that, the take-home message, is that anything on the left can be used to make anything on the right, but anything on the right cannot be used to make anything on the left unless you go back through a carboxylic acid. And that's really the take-home message. These are more reactive, these are not, and if we want to make this, we're going to have to go back from an amide all the way back into an acid chloride. Let's take a look. If we wanted to take this species right here, and we wanted to make this species right here, we could easily accomplish that in one step because the ester is less reactive than the acid chloride. And in order to accomplish this, all you would need to do is identify the species that you are adding, which is this OCH3, turn it into a decent nucleophile, and when we deal with acid chlorides, we need pyridine present, and that is the way that you would synthesize an acid chloride, an acid chloride, and from an acid chloride synthesize an ester. Let's take this idea one step further. If you wanted to start with an ester and react it to make an acid chloride, you could not simply add you could not add chlorine to that solution because the chlorine is not a strong enough nucleophile to displace that OCH3. And so you would not be able to accomplish it. Not a single step wherein you could just envision using like NaCl as your nucleophile. That would not work because this acid chloride is more reactive than its corresponding amide and ester. And in order to accomplish this, you would have to first convert this into a carboxylic acid using acidic or basic conditions. I'll use basic conditions here. And then you would have to react that in the presence of SOCl2 to convert this species into its corresponding acid chloride. Things that are less reactive as far as carboxylic acid derivatives are concerned cannot be easily converted back into their more reactive species. They have to go back into this carboxylic acid in order to react and form species to the left. And so that is the most important take-home message here. I would also like to explain one and only one thing to you, which is the important aspect of the work that's being done in my research laboratory. You will see that there is no direct way to make a carboxylic acid and convert it into an amide right here. This carboxylic acid and this to form this amide. And so let's just walk down this to kind of illustrate some important aspects. If you wanted to take a carboxylic acid and convert that species into an amide, like this, you could not simply add RC double bond OOH plus NH2R, because the reaction that would take place here would be to deprotonate that carboxylic acid and protonate the corresponding base, which is the amine. This reaction is what would take place if you were to mix those two species together. So there is no, not a direct single step route. Okay? Well, what happens here is that in order to synthesize this amide, you would have to first convert this into maybe an ester using, let's use acidic conditions. And in this case, we could use methanol, CH3OH, in the presence of acid, to convert this into an ester, which then you could react with an NH2R to produce our amide. It would require two steps in order to convert a carboxylic acid into an amide, and likely in this one step, you would lose this reaction right here to convert a carboxylic acid into an ester. This right here, this takes about, let's see, typically under acidic conditions 8+ hours, and you'll get about 90% yield. And then conversion of this ester into this amide typically would take about 12 hours, and you would get about 85% yield. And so just a little bit of math, 0.9 times 0.85 gives you an overall yield. You would, in overall, after two steps, you would end up losing 25% of your product roughly. You would get a 76.5% conversion, of which you would likely lose some of your compound to the purification process. And you would also take, what, 12 plus 8 is 20 hours to do so. And so that kind of demonstrates what you would need to do in order to convert a species into an amide, a carboxylic acid into an amide. You got to convert it into a more reactive species and then convert it into the amide, because there is no direct route to convert this carboxylic acid into that amide. Check this out, people. This right here is the method that you use to make peptides. And one of the peptides that is really pervasive right now is Gardasil, a HPV vaccination. And likely some of these COVID-19 vaccinations are also going to be peptides. And this kind of just shows you the general process by which you would make an amide from a carboxylic acid to make a peptide in this example. Here's something that I want to just briefly share with you about, and this is something that I like to crow about, not because I've done it, but because students in my research laboratory have done it, and people like to think that if you're outside of the research triangle, no amazing research happens. Well, let me show you something. Your textbook says there is no way to convert a carboxylic acid into an amide. In my research group, we are able to directly convert a carboxylic acid into an amide. We are able to do that in 3 minutes at 100% conversion. Fascinating. No wonder we have so much interest from all of the major pharmaceutical companies in the world right now in our research. So this ties in just a little bit of the main idea that I want to share with you, which is simply this. There is a reactivity that is to be considered when you look at carboxylic acid derivatives, and when you think about using them in multi-step synthesis, if the requirement is to make something to the left of what you already have, you cannot simply substitute the thing here, the chlorine, for the OR, because this will not outcompete this on the molecule. And as a result, if you want to synthesize anything to the left, you must go back to the carboxylic acid to synthesize that acid chloride. And one other part that you just learned is that there are some new direct routes that have never been made in the history of organic chemistry that allow us to do things that you haven't seen before in my research lab, done by undergraduate research students that are now starting a company with me to try and get this science out there into the world. It is our hope that we will be able to produce peptide vaccinations for the world faster than anybody else has in the history of mankind. That's all I have to say about carboxylic acid derivatives. I hope this helps.